The formula for momentum is P equals mass times velocity. Because velocity is a vector, so is momentum. Momentum will always follow the direction of the velocity. And in the global SI system, momentum is measured in kilograms times meters per second. It doesn't have a special name like watts or joules. And because it's connected to mass, that means the more mass, the more momentum. For example, let's say you had two baseballs and they're traveling in the same direction. One's going at this speed, one's going at this speed. Which one's got momentum more, the faster one? What if you had two airplanes and this one here is heavier than this one here? Which one has more momentum if they're traveling at the same speed? It's the heavier one. Because of Newton's laws, to change the momentum of an object, a force is required, some kind of force in some way. Newton's second law was actually originally stated in terms of momentum. We all know it as F equals ma. But when Newton first wrote it, it was F equals the change in momentum over the change in time. So this means that the rate of change for momentum, the speed at which it changes, is equal to the net force being applied on whatever object you're talking about. Now, before we go into examples and problem solving, for fun, I'll show you how we derive the normal version of Newton's second law from this. So it's F equals the rate at which momentum changes. And momentum is mass times velocity, right? So we can write the change in momentum as the final mass velocity minus the initial mass velocity divided by change in time. Factor out mass because mass is constant here. You get mass times the change in velocity divided by change in time. This is also written as mass times delta velocity, delta time. And what is this? If you notice, this is the formula for acceleration. So you get mass times acceleration. F equals ma. Let's go through a problem. Imagine for a second you're a pro baseball athlete. This is you. And baseball people wear hats, so you have a hat. You hit a ball with a bat, and when the ball, after being hit, just leaves contact with the bat, it's hit at 50 meters per second. The ball itself is 150 grams. And let's say the ball is in contact with your bat for 3 milliseconds. What's the average force on the ball? Okay, first we have to do some unit conversion. 150 grams is 0.150 kilograms. And 3 milliseconds is 3 times 10 to the power of negative 3 normal seconds, which is 0.03 seconds. And what are we looking for? We're looking for the force on this ball. And we have the mass and the velocity. So let's use our new formula. Change in momentum divided by change in time. Change in momentum would be the final momentum. So the momentum just after ball leaves contact with the bat. Minus the ball at the start, which is when it gets hit. Divided by the change in time, which is this many seconds. That's how long it's in contact with the bat. If you go and plug in your values, then you get roughly 2,500 newtons of force. And we say roughly because we're neglecting gravity. If you went and solved for how much force gravity is doing on this ball, it would be a very small number, so we don't have to consider it at all, especially since the time interval is so small. So you smack the ball with this much force, and that's a lot of force, 2,500 newtons. For reference, to lift up a 60 kilo human, it's only about 600 to 800 newtons of force required. Let's go through another problem. Imagine for a second that you're a firefighter, and there's burning buildings on fire because it's burning, and from your awesome fire truck, there's a hose, and you use this hose to shoot water at this fire. The water is shot out horizontally at 15 kilograms per second with a speed of 30 meters per second. Assuming the water is stopped completely when it hits the wall, without splashing back, what's the force the water is exerting on the wall? We can do a similar thing to the last problem. We're looking for force, which is momentum over time. But here's where we have to do a bit of thinking. Change of momentum is the final momentum minus the initial momentum. What's the final momentum? The final momentum is 0 because the water gets stopped. Well, what's the initial momentum? We know that momentum is mass times velocity, but we're not given an explicit, we're only given this, the fact that every second that passes, 15 kilos of water leaves the hose. So let's use this as our time interval, 1 second, and this as our mass. 15 kilos per second multiplied by the velocity, 30 meters per second, divided by our time interval, which is 1 second. And this is equal to 450 newtons when we neglect gravity, when we assume that the effects of gravity are negligible. For every topic I cover, I like to create a free cheat sheet, and I use them myself as well. So if you want your own with all the formulas you'll ever need in one place, then go sign up in the description.